So we've seen that the electric field inside a conductor is always equal to 0. We've also seen that the potential difference between 2 points is related to the electric field through delta V is equal to minus the integral of E dot ds, which tells us that the potential difference between any 2 points in a conductor where E is 0 is 0. So there is no potential difference between any 2 points inside a conductor. Now, if you've played around with circuits before, you are probably aware that if you connect a wire from one point on a circuit to another point, then as long as that wire is conducting, you're forcing those 2 points on the circuit to be at the same voltage. And this is why you've now connected them with a conductor. So we can actually use this along with what you've already learned to solve some pretty fun problems. So let's have a look at one such problem now. So the problem we're going to set about solving is a conducting plate with a surface charge density sigma and width A is inserted between two neutral conducting plates, a distance d on 4 below the top plate, plate 1, and a distance 3d on 4 above the bottom plate, plate 2, as shown in the figure. Plate 1 and plate 2 are now joined with a conducting wire. What is sigma 1 and sigma 2? The charge densities induced on the two plates. And we can assume that all the plates are large, so end effects can be neglected. So a useful thing to remember is that previously we have derived the expression for the electric field around a large plate, and the electric field is equal to the charge density divided by 2 epsilon naught. So let's consider what the electric fields are going to look like in our configuration here. Well, when we insert a plate with charge sigma, let's assume that sigma is positive. Then because it's closer to the top plate than the bottom plate, the top plate is going to end up with an induced negative charge, while the bottom plate will end up with an induced positive charge. So we know that these two have to have opposite charges because this system was initially neutral. So in fact, we can write sigma 1 plus sigma 2 is equal to 0. And this one's going to be negative. And this one here is going to be positive. So let's represent sigma with this blue color. And let's sketch what the electric field is going to look like in all these regions. So because this is a positive charge, electric field lines go away from positive charges. So the electric field lines due to the inserted charges are going to look like this. Now, one of the nice things about the electric field around charge plates was that it didn't drop off with distance. There was no distance relationship. So this electric field due to the plate with the charge density sigma has a magnitude given by sigma over 2 epsilon naught everywhere. So that's the value it has in each of these regions, and we've shown the direction. So let's now consider the top plate, and we'll color sigma 1 red, and we've said that sigma 1 is negative. So because it's negative, the electric field is going into that plate. So it's always pointing towards the top plate. And so we can write the electric field here as equal to sigma 1 over 2 epsilon naught, and the directions given in the diagram. And then we'll let the third plate down here, it has sigma 2 on it, and we'll color it green. And we've said that this is positive, so the electric field is going away from this plate. So it's going up here, and up here. And we can write, well, the electric field is given by sigma 2 over 2 epsilon naught. And now let's number each of these regions. So we'll call this top region here region 1. We'll call the next one region 2. we'll call this one region 3 and this one down here below the second plate region 4. Now, in fact, we don't need to consider regions 1 and 4 to solve this question, but let's just consider what the electric field is there anyway. So in region 1, we've got the electric field due to the inserted plate going up, and then the electric field due to these two plates, plate 1 and 2, one is going up and one is going down. And they're given by sigma 1 on 2 epsilon naught and sigma 2 on 2 epsilon naught. So you can see that because of this expression, which tells us that sigma 1 is equal to minus sigma 2, these two have the same magnitude, then these electric fields have the same magnitude but opposite directions, so these two must cancel out. So in region 1, we've got that E1, let's call this one E1, and E2 cancel out as they have the same magnitude but an opposite direction. So that tells us that the electric field in this region is just this blue one. So the electric field is equal to sigma over 2 epsilon naught, and that is up. Now, the same argument holds in region 4. You can see the green and the red are in opposite directions and they've got the same magnitude. So in region 4, only have E equals sigma over 2 epsilon naught. So this tells us that E is equal to sigma over 2 epsilon naught, and in this case it's down. Okay, so we didn't have to do this for the problem, but we've done it anyway. Now, for solving this problem, we will care about the electric fields in region 2 and region 3. So in region 2, electric fields obey the law of superposition. So we can say, well, the electric field is equal to, now they're all in the same direction, and technically sigma 1 is negative, which is just going to confuse everything. So let's write everything with absolute value signs, and we've accounted for the direction here. We've drawn on the direction, so that accounts for those negative signs. So in region 2, the electric field is given by the electric field due to the inserted plate, which is sigma over 2 epsilon naught. And then we've also got the electric field due to the top plate, which is sigma 1 over 2 epsilon naught. And then the electric field due to the bottom plate, which is sigma 2 over 2 epsilon naught. And in this case, this is up. And in region 3, so that's this region here. So you can see here, the electric field due to the inserted plate is going down, while the ones due to the top and bottom plate are both going up. So we can say, well, the E in this region is given by minus sigma over 2 epsilon naught plus sigma 1 over 2 epsilon naught plus sigma 2 over 2 epsilon naught. And this is also up, which is why I've written this first one with a negative sign, because it's going down. Now, we're told that plate 1 and plate 2 are joined with a conducting wire. So physically, that means that there is no potential difference between plates 1 and plates 2. So as plate 1 is joined to plate 2 with a conducting wire, the potential difference between them is equal to 0. So we can write that the potential difference, which is equal to, we're considering moving from plate 1 to plate 2, so that's the voltage at plate 2 minus the voltage at plate 1, which we've said is equal to 0, but we can also express this in terms of the electric field, because we've got that the voltage difference is equal to minus the integral of E dot ds. So we're taking ds down like this. We're moving from the top plate down to the lower plate. And so this is equal to minus the integral. So we're going from plate 1 to the inserted plate here. So we start at, it's in terms of ds, so we're considering displacement. So we start at 0 displacement from the top plate and we get down to d4, and that's the electric field in this region. So let's call that E2. So I'll put a little 2 here, the little 3 here to distinguish them. That's the electric field described by this, ds. So you can see that because this is going up and ds is going down, when we take the dot product between those two, that's going to give us a negative sign, but we'll include that in a second. And then when we're inside the conducting plate in here, because it's a conducting plate, there is no electric field in here. So plus 0, and that 0 is because there's no field inside a conductor. So then we go from this point here, which will be A plus D on 4, to this point down here, which the distance from here to here is going to be D plus A. So that'll be minus the integral from D on 4 plus A to D plus A of the electric field in region 3 ds. Okay, so let's do this integration now. So we know that 0, because we've said this is equal to 0, when we integrate this, we just end up with the electric field times the displacement. They're in this region, they're in opposite directions, so we're always going to end up with negative. So we've got this negative out the front already. That's from this one. And then for this first plate, we'll end up with negative sigma over 2 epsilon naught, and then that's times the distance. For the second plate, it'll be minus sigma 1 over 2 epsilon naught times the distance. And for the third plate, it'll be minus sigma 2 over 2 epsilon naught times the distance. And the distance is 0 to D on 4. And then this one's just 0, and then we've got negative. Here we've got, so we're still going down. So this first term in this case is actually positive because they're in the same direction. So we'll have sigma over 2 epsilon naught s. And now the rest of the terms are in the opposite direction again. So minus sigma 1 over 2 epsilon naught s. Minus sigma 2 over 2 epsilon naught s. And this is going from D on 4 plus A to D plus A. So now we can sum these into the limits on our integral. So we've got minus, this will be sigma over 2 epsilon naught. Still got a negative sign, and then it's D on 4. Then we've got minus sigma 1 over 2 epsilon naught D on 4. And then we've got minus sigma 2 over 2 epsilon naught times d on 4. And then when we substitute in 0, each of these terms becomes 0. So that's easy. We don't need to worry about those ones. And then we've got this second bracket. So in this first term, we've got sigma over 2 epsilon naught, and then we've got d plus a. And then minus sigma 1 over 2 epsilon naught d plus a. And then minus sigma 2 over 2 epsilon naught times d plus a. And then we substitute in the second one and subtract it off. So we have got minus sigma over 2 epsilon naught, and this will be d on 4 plus a. So hopefully you can see with this a, we've got a negative sigma 2 epsilon naught a here, and a positive sigma 2 epsilon naught times a here. So these a's are going to cancel off. And then the next term will be plus sigma 1 over 2 epsilon naught d on 4 plus a. And again, the a's cancel each other off. And then finally, we've got plus sigma 1 over 2 epsilon naught d on 4 plus a. Our a's cancel off. And that's that bracket. And this is equal to 0. So let's use that to simplify this now. Each of the terms has a 2 epsilon naught and a d in it now that we've cancelled out all those a's. So let's cancel all of those out. So we can do this because it's equal to 0. Okay, the other thing I'd like to do is multiply everything through by 4 because we've got a lot of divides by 4s. So when we multiply this term by 4, that disappears, that will disappear, that will disappear. When we multiply this one by 4, we'll need to put a 4 in front. This one here will also have a 4 in front. This one here will have a 4 in front. But this one here's got a 4 down the bottom, so that will cancel, and that will cancel. Okay, so now let's write down what we've got left. So this first term, we've got a negative and a negative. So that is just sigma. And then we've got a negative and a negative. So that's plus sigma 1. And then again, we've got a negative and a negative. So that is plus sigma 2. And then we've got, here we've got 4 sigma, and here we've got minus sigma. So this one here is going to be minus 3 sigma. And then here we've got minus times minus, so that'll be plus 4 sigma 1, and then minus times plus, so minus sigma 1. So that'll be plus 3 sigma 1. And then with the sigma 2's, again, we've got plus 4 sigma 2 minus sigma 2, so that's plus 3 sigma 2. So then we can simplify this a bit further. Let's combine the sigmas. We've got minus 2 sigma, and then we'll combine the sigma 1's. So we've got plus 4 sigma 1, and then we'll combine the sigma 2. So again, we've got plus 4 sigma 2. Now remembering up here, we said sigma 1 plus sigma 2 equals 0, which tells us sigma 1 equals minus sigma 2. But we know that the magnitudes must be the same. So we've got that the magnitude of sigma 1 is equal to the magnitude of sigma 2. So let's replace this sigma 2 with sigma 1. So we can write this expression here as this is equal to minus 2 sigma plus 8 sigma 1. And so just rearranging this, we can divide by 2, and so this becomes 4, and we end up with sigma is equal to 4 sigma 1. And we've already discussed how the signs compare. We've said that sigma 1, because it's closer to the plate here with the charge on it, is going to have a negative charge induced on it if this charge is positive. So it'll have a charge induced on it with the sign opposite to the inserted charge. So we know that physically this means sigma is equal to minus 4 sigma 1. And because sigma 1 and sigma 2 have the same magnitude but opposite sign, we can say this is equal to 4 sigma 2. So to answer the question, a charge density sigma 1 is equal to negative sigma over 4 is induced on plate 1, while a charge density of sigma 2 is equal to plus sigma over 4 is induced on plate 2. So you can see how we've used an awful lot of what we've learned so far to answer this question here, which is pretty cool.